Hello and welcome to this online lecture. My name is Patty Kokish and I teach Math 136 in the Northwest region and online. Today we're going to go through some week 12 topics from online Math 136 for Ivy Tech. So we're going to start with section 6.4, which is all about logarithmic functions. So if you recall, a one-to-one function y equals f of x has an inverse that's defined implicitly by the equation x equals f of y. In particular, the exponential function y equals f of x equals a to the x, where a is greater than 0 but not equal to 1, is going to be one-to-one, and hence has an inverse function that is defined implicitly by the equation x equals a to the y. And again, a has to be greater than 0 but not equal to 1. This inverse function is so important that it's given a name, and it's called the logarithmic function. The logarithmic function to the base a, where a is greater than 0 and not equal to 1, is denoted by y equals the logarithm to the base a of x, or log base a of x. And it's defined by y equals log base a of x if and only if x equals a to the y. So this is an important property to have memorized. My suggestion would be to put y equals log base a of x on one side of a note card and x equals a to the y power on the other side to make sure that you understand this. The domain of the logarithmic function is going to be anything where x is greater than 0. Now, in this case, that's because we have log base a of x. What we need to have happen is whatever we're taking log of, that needs to be greater than 0. So you'll see that this gets a little more complicated in just a bit. Okay, so if we look at this, if we have y equals log base 3 of x, what we say is that x equals 3 to the y power. So what I want you to notice is, for some people who are visual, it's kind of easier if you imagine the numbers sort of floating into place. So if you look at the base of the log, it's 3, and that's the base of your exponent over here. And then the number that was by itself, in this case it's a y, that becomes your new power. Okay, so it goes base to the number that was by itself, and then that's going to be equal to the number that wasn't by itself before. So x equals 3 to the y. So for example, 4 equals log base 3 of 81. That's equivalent to saying that 81 is equal to 3, because that's our base, to the 4th power, because that was by itself. So we know 3 to the 4th power is 81, so this is an equivalent statement. All right, if y equals log base 5 of x, then what we say is that x equals 5 to the y power. So this is the same as the first one, we just have a 5 instead of a 3. The 5 is our base, so 5 is our base over here. The y was by itself, so that becomes our exponent, and then we're just left with this equals x. So for example, negative 1 equals log base 5 of 1/5. That would be equivalent to saying that 1/5, that's what we're taking log of, equals 5, which was our base, to the negative 1 power. And that is true. Okay, so the first thing we're going to do is change exponential statements into logarithmic statements, and then we're going to go from a logarithmic statement into an exponential. So let's say we have this, 1.2 to the 3rd power equals m. We have our rule down here. This is the one that I suggested you put on a note card. So if we have 1.2 to the 3rd equals m, 1.2 is our base, so we know that's going to be our a, okay? And then the m, that was by itself, so that's going to be our x, and then our power is going to be our y. So in this case, we have 3 equals log base 1.2 of m. All right, if we have e to the b equals 9, what we would have here is b, that's our power, equals log base e of 9. And here we have a to the 4th equals 24, so that means that 4 equals log base a of 24. Okay, now we're going to go the other way around. So it's the same idea, but this time we're given a logarithmic expression and we want to change it into an exponent. All right, so we have log to the base of a of 4 is equal to 5. So that would change into a to the 5th, it's our base, to the 5th power is equal to 4. If we have log base c of b equals negative 3, And if we change that, it's going to be e to the negative third equals b. Okay, so you see you're just rearranging these things. One thing you can do is just memorize this rule, figure out what your a, your x, and your y are, and then just rearrange them until you get what you want. And for c, we have log base 3 of 5 equals c. So we're going to have 3 to the c power equals 5. It just takes a little bit of practice to kind of catch on. It's really just figuring out what your a, your x, and your y are, and then plugging it in. Okay, we can also evaluate logarithmic expressions. So if we have something like this, log base 3 of 81, what we would do for that one is we would want to ask ourselves, 3 raised to what power gives us 81? That's really what this is asking. So we can write it as y equals log base 3 of 81. That's going to be what we're trying to find is our y. And then we change it into an exponential function or expression. And so we have 3 to the y equals 81. Now if you think about 81, we know that's 3 to the 4th power. So we can rewrite this as 3 to the y equals 3 to the 4th. And then once we have the same base, essentially what you can do is just ignore them, because once you have the same base, we know that the exponents have to be equal. So we just end up with y equals 4. So we know that log base 3 of 81 is equal to 4. Okay, for b, we have log base 2 of 1/8. That's saying that 2 raised to what power yields 1/8. So again, we write this with a y equals log base 2 of 1/8. And then we rewrite this with an exponent, so we say 2 to the y equals 1/8. And then we know that 8 is 2 cubed, so we rewrite this as 1 over 2 cubed. And we should know that when we have something that's in the denominator, when we have an exponent in the denominator, what we can do is we can make it negative and move it to the numerator if it's already positive. So in this case, we have 2 to the negative third power. So we have 2 to the y equals 2 to the negative third. And again, we end up with the same bases. So what we're allowed to do is just ignore those bases because we know that the exponents have to be equal. So we get y equals negative 3. Therefore, log base 2 of 1/8 is equal to negative 3. Okay, we can also determine the domain of a logarithmic function. So we talked very briefly about this when we were going through what a logarithmic function is. But we know that the domain of a logarithmic function should be the same as the range of an exponential. Now, you may ask yourself how we know that. And we should know it because we know that exponential and logarithmic functions are inverses of one another. And you should remember from a previous chapter that the domain of something is the same as the range of its inverse. So in this case, we know that the domain is going to be from 0 to infinity, not including 0. And we know that the range should be all real numbers, since the domain of an exponential is all real numbers. Okay, so if we have y equals log base a of x, again, the defining equation is x equals a to the y. A different way to write this would be x is between 0 and infinity, not including 0, and the range is between negative infinity and infinity for your y. Okay, so if we want to find the domain of some logarithmic functions, what we can do is basically take whatever you have log of. So in this case, we have log base 3 of x minus 2. So the x minus 2, that's our important part. What we need to have happen is we need x minus 2 to be greater than 0. If you try typing log of 0 in your calculator, you're going to get some kind of domain error. Same thing is true if you type log of any negative number. So we know that whatever we're taking log of has to be positive. So what we do is we set our x minus 2 greater than 0. And then we go ahead and just solve. So we would add 2 to both sides, so we'd get x is greater than 2, which if you're writing it in interval notation is going to be from 2 to infinity. Now, of course, it gets more complicated. So if we have something where we have x plus 3 over x minus 1, that's what we're taking log of, what you have to do is you have to set that greater than 0. And then what you need to do is either graph your rational function or set up a number line and then solve it using the same rules that we used back in chapter 5. And if you do that, you should get negative infinity to negative 3 and 1 to infinity. And then for this one, we have absolute value of x minus 1. Now, we know that the absolute value of the function of x minus 1 is never going to be negative because we have an absolute value, which always makes it positive. But we know that x minus 1 cannot equal 0 because if we have absolute value of 0, then that's still just 0, which causes a problem. So we know that we get all numbers except x is equal to 1. So in interval notation, that would be from negative infinity to 1, union 1 to infinity. So essentially, anytime you're finding domain of a logarithmic function, you're going to take whatever you have log of here, okay? You can ignore the base, it doesn't really make a difference in this case. And you just set that greater than 0 and then use previous rules that you've learned maybe from chapter 5 or all the way back from the beginning in order to solve that. Okay, we can also graph logarithmic functions. So this is, it's not easy, but it should be fairly simple given that you already know how to graph exponential functions. So if you look at this blue graph here, this should look familiar. Just ignore the pink for right now. But if we look at this blue, this should look pretty familiar. That's just y equals a to the x, which was from our last chapter, when a is between 0 and 1. So when a is a fraction like 1/2 or something like that. So you get this decreasing function that you see in blue. Now, if you remember, inverses have a very nice property, and that is if you take the line y equals x and you use that as your symmetry line. So if we take this blue line and we flip it across our line y equals x, we end up with what you see in pink here, which is our logarithmic function. So we have log base a of x. Now this is, again, for a between 0 and 1. So you'll see that this is also a decreasing function, but it's kind of flipped around a little bit. And then over here, if we look at this blue graph, this one should look familiar as well. This is, again, an exponential function that we've already done, where a is greater than 1. So some number like 2 or 3 or 4 or 100, doesn't really matter. So that's our exponential blue function. And then again, since we know that exponential functions and logarithmic functions are inverses of one another, if we take this blue graph and we flip it across our line y equals x, we end up with this pink one over here, which is the graph for y equals log base a of x, where a is greater than 1. And this one's an increasing function. So for example, we can have actual numbers in here as well. So if we have y equals 2 to the x power, we can sketch like a nice little graph just by picking some points. If we pick 1 for x, we get 2 out for y. If we pick -1 for x, we get 1/2 out for y. If we pick 0 for x, we get 1 for y. And what you'll see is we end up with this blue graph, which looks very similar to the one that was on the right for the previous slide. And then we don't really have to do anything except interchange our x's and our y's, or you can flip across this line y equals x, and we end up with our graph for the equation y equals log base 2 of x. The same thing can be said for anything when we have a fraction. So for example, if we have y equals 1/3 to the x power, that's an exponential function. We know that our a is between 0 and 1, so this one's going to be one of the decreasing ones, okay? So again, if we plug in some points, if we plug in 0 for x, we get 1 for y. If we plug -1 for x, we get 3 for y. If we plug 1 for x, we get 1/3 for y. So we can go ahead and graph that blue line. And then again, you can either think of it as flipping your x and y coordinates around or flipping across the line y equals x, and you end up with this pink graph right here, which would be the graph for y equals log base 1/3 of x. So we have a list of properties for logarithmic functions, the same way that we did exponential. The domain is going to be the set of positive real numbers. The range is the set of all real numbers. So if you remember from your exponential functions, this is actually flip-flopped, okay? The x-intercept of the graph is 1. There is no y-intercept. And the y-axis, which would also be the line x equals 0, is going to be a vertical asymptote of the graph. So instead of having a horizontal asymptote, now we have a vertical asymptote. A logarithmic function is decreasing if a is between 0 and 1, and increasing if a is greater than 1. And it's always going to contain the points 1, 0, a 1, and 1 over a, -1. And again, just like exponential graphs, it's smooth, continuous. It doesn't have any holes or corners or gaps or anything like that. Now we also have something called the natural logarithmic function, which we're going to talk about a little bit more later, but this is really important. E is just a number, okay? It's about 2.72. It's a very nice number. It's kind of like pi. It has a lot of applications, very useful in math. So it's something that you see quite a lot. So if we think about the graph of the equation y equals e to the x, I think this is something we talked about when we talked about exponential equations. You'll see this graph in blue right here, which looks very similar to something like y equals 2 to the x or something like that. Now if we take this and we flip this across our line y equals x, or interchange our x's and our y's, we end up with y equals ln of x. This is the natural log, okay? Ln stands for log natural. And we know that this is true, y equals ln of x, if and only if x equals e to the y power. Okay, so this is kind of a special function. Again, this is something I would put y equals ln of x on one side of a note card and x equals e to the y on the other, and just carry them around with you, flip them back and forth until you know those. Okay, so let's work on graphing a logarithmic function. So for this one, we're not going to graph its inverse, but we want to find the domain, graph our function f, and then from the graph determine the range and the vertical asymptote. I don't know why this thing keeps popping up. Let me hide this. I don't know if there's a question. No, it doesn't look like it. Okay. So if we think about what we know y equals ln of x is going to look like, it's going to look something like this blue line here, okay? And again, we can plug in some points, see how that works, but it's going to look something like this blue line here. And then what we can do is we can just use transformations. So we know that we've multiplied by -1 because we have this negative out front. So that means we're reflecting around our x-axis. So if we take this and we flip it basically upside down, so it's been flipped across our x-axis, we end up with something like this, which would be the equation y equals -ln x. And then we know that this -2, this is the one that's a little bit counterintuitive to some, but this one moves it to the right too. So all we do is we take our graph that's in our middle and we move it to the right too. So if you look at this, the domain is going to be all real numbers. Oh, sorry, the range is going to be all real numbers, -infinity all the way up to infinity. The domain is going to be from 2 to infinity, not including 2, because we have an asymptote at x equals 2. That's going to be our vertical asymptote. Okay, so common logarithmic function is just y equals log of x. Now, if you see that, that means that there's an implied base that's 10, okay? And if you just type log into your calculator, what you'll find is that it's already in base 10, okay? So that's what your calculator deals with, and a lot of times that's what we're dealing with as well. But that implies that x equals 10 to the y power. And we can look at these graphs as well. Our exponential function that would go with that would be y equals 10 to the x power, and here we have our pink graph, that's our log of x. Again, the implied base is 10. Okay, let's graph another. Let's say we have 3 log of x minus 1. So for this one, we start with log of x. We replace x with x minus 1. So if you remember this -1, that moves it to the right one. So we've shifted our entire graph to the right one. You'll notice the asymptote moved with it as well. And then we multiply by 3, which just vertically stretches it by a factor of 3. So it kind of makes our graph a little bit taller. So you'll notice we have some points here as well. You'll notice we have a vertical asymptote at x equals 1. The range is going to be from -infinity to infinity, but the domain is going to be from 1 to infinity, not including 1. Now, if we look at the inverse, this would be pretty easy to do at this point because we already have our blue graph, which is f of x equals 3 times log of x minus 1. So the inverse would be f inverse of x is equal to 10 to the x over 3 power, or 1/3 x power, plus 1. So this would be obtained by interchanging your x and y and solving for y. And we notice here where we had a vertical asymptote before, we now have a horizontal asymptote. Okay, we're going to solve some more logarithmic equations closer to the end of this chapter in 6.6, which we'll get to at the end of today. But let's start with a couple of, I hate to say easy ones, but they are a little easier. All we really have to do for these is just change them into exponential equations. So we have log base 2 of 2x plus 1 equals 3. we want to go ahead and change it into exponential form, because when it's in this form, we don't really know what to do with it at this point. So you just want to rewrite it. This is your base, this 2. So you have 2. This is your exponent, if you recall. So we have 2 to the third equals 2x plus 1. Now this is actually quite nice now, because we know that 2 to the third is just 8. So we have 8 equals 2x plus 1. And then if we solve this, we would subtract 1. We would get 7 equals 2x. Divide by 2, so we get x equals 7 halves. Now you always need to check these, okay, because we can run into some issues here, particularly with our denominator. A lot of times when we end up with two solutions, one of them ends up being extraneous, which is kind of the same thing that happened when we did our rational equations. So in this case, if we plug 2 in, we just have 2 times 7, or sorry, if we plug 7 halves in, we just have 2 times 7 halves plus 1. So we just get 8. Log base 2 of 8, that's going to give us 3. So that's not a problem. Now this one here, log base 3 of 343 equals 3. So we change this into an exponential. So we get x to the third power. All right, this was our base, so it's our base down here. This was by itself, so it's our exponent. So we have x to the third equals 343. Now these will take you guys a while to get used to, but it's actually going to be 7 to the third power that gives you 343. Now the way that you can solve this is just take the cube root of both sides. And in order to check this, if we take log base 7 of 343, we will get 3. And you don't know how to do this in your calculator yet, but we're going to learn something called the change of base formula in just a little bit that will show you how to do that. Okay, we can also use logarithms to solve exponential equations. So let's say we have something like this. 2 times e to the 3x power equals 6. So you always want to get the exponential, whatever you're talking about that has the exponent attached, you want to get that by itself. So in this case, we want to divide both sides by 2. So we get e to the 3x equals 3. And then we want to change it back into logarithmic form. So in this case, it would be ln of 3 equals 3x. And then in order to get x by itself, we divide both sides by 3. So we get ln of 3 divided by 3 is equal to x. That would be our exact solution. And then if you want the approximate solution, what you'll do in your calculator is you'll type in ln of 3. Okay, you should all have an ln button. And then once you've evaluated that, you go ahead and divide by 3, and you should get something around 0.366 as your approximate solution. So on MyMathLab, a lot of the problems are set up where you'll first enter an exact solution like this, okay, that will have a log in it or a natural log, and then you'll also enter an approximate solution. Okay, blood alcohol concentration, or BAC, is a measure of the amount of alcohol that's in a person's bloodstream. A BAC of 0.04% means that a person has 4 parts alcohol per 10,000 parts blood in the body. Relative risk is defined as the likelihood of one event occurring divided by the likelihood of a second event occurring. For example, if an individual with a BAC of 0.02 is 1.4 times as likely to have a car accident as an individual that hasn't been drinking at all, then the relative risk of an accident with a BAC of 0.02 is 1.4. So recent medical research suggests that the relative risk, or R, of having an accident while driving can be modeled by an equation of this form, R equals e to the kx power, where x is the percent of concentration of alcohol in the bloodstream and k is some constant. So the first thing we need to do is actually find k. So it tells us up above that 0.02% corresponds with an R, or a relative risk of 1.4. So we need to substitute those in. So we get 1.4 equals e to the k times 0.02 power. And then we change this into logarithmic form. So we have 0.02k equals ln of 1.4. And then divide both sides by 0.02. So we get k equals ln of 1.4 divided by 0.02. This would be your exact answer. And your approximate answer would be 16.82. So now we can use that value. And let's say we want to find the relative risk if the concentration is 0.17%, which is pretty high. So what we're going to do is we're going to plug in 0.17 into our equation. So we have e to the 16.82 times 0.17 power. Make sure if you're doing this in your calculator that you put parentheses around your exponent. And you should get about 17.5, so that's our relative risk for someone who has a 0.17% blood alcohol content. or concentration. So for a concentration of alcohol in the blood of 0.17%, the relative risk of an accident is about 17.5. That means that a person who has a blood alcohol concentration of 0.17 is more than 17 times as likely to have a car accident as a person who has no alcohol in their bloodstream at all. So let's say that we want to use the same value of K and we want to know what blood alcohol concentration corresponds to a relative risk of 100. So what we would do is we'd substitute 100 in for R, again change it to a logarithmic equation. So we have 16.82x equals ln of 100, and then divide by 16.82 and we get 0.27. So it means that for a concentration of alcohol of 0.27%, the relative risk of an accident is 100. So let's say the law asserts that anyone with a relative risk over 5 or more shouldn't have driving privileges. So we want to know at what concentration of alcohol should a driver be arrested and charged with a DUI. So what we would do is we'd substitute 5 in for our R, which is our relative risk. Again, change it into a logarithmic equation, so you get 16.82x equals ln of 5, and divide by 16.82, and we get 0.096. So that means that a driver with a BAC of 0.096% or higher should be arrested and charged with a DUI. Now, of course, this varies by state, but this is just an example. Okay, so here's a nice summary of the properties of a logarithm. Domain is going to be from 0 to infinity. Range is all real numbers. The x-intercept is 1, but there is no y-intercept because there's a vertical asymptote at the y-axis, which is the line x equals 0. We know it's going to be increasing if we have some number where a is greater than 1. And then the only difference here is that we know it's going to be decreasing if we have some number between 0 and 1 for our a, so like 1/2 or something like that. Okay, so let's move on to section 6.5, which talks about some of the properties of logarithms. So let's establish a couple of nice properties first. The first is going to be that log base a of 1 equals 0, and this one's pretty easy. If we change this so that let's pretend like we don't know that it's 0, let's say y equals log base a of 1. What we can do is we can change this into an exponential equation. So we have a to the y equals 1. And if you think about this, we know that a to the y is going to be equal to a to the 0 power because any number to the 0 power just gives you 1. And now we have the same bases, so what we can do is we can just set the exponents equal to one another, so we just get y equals 0. So this shows that log base a of 1 is equal to 0. And over here we have log base a of a equals 1. If we'd like to show that, again, we're going to ignore this one part, pretend like we don't know that, and we are going to call that y. So we have y equals log base a of a. And then we change this into an exponential, so we have a to the y power equals a. And you should note that anything to the first power is still just going to be that number. So we change this so that we have a to the y equals a to the first, and then ignore our bases, so we just have y equals 1, which shows us that log base a of a is equal to 1. So those are a couple of the properties. We also have some other nice properties. In the properties given next, m and a are going to be positive real numbers. A is not 1, r is going to be any real number. The number log base a of m is the exponent to which a must be raised to obtain m. So what that means is that if we have a to the power log base a of m, then that's going to be equal to m. The logarithm to the base of a raised to a power is equal to that power. So if we have log base a of a to the r power, then that's just going to be r. So let's use a couple properties. Let's say we have log base pi of pi to the third power. This actually follows a property on the previous page. This log base pi of pi, you can kind of think of that as sort of canceling one another out, so you're really just left with this exponent here, which is just 3. And this is one where we have a base to the power with the log. Looks pretty confusing, but if you look at this base and this base are the same, so again, this is kind of, I hate to say cancel out because it's not really canceling, but the property just tells us that we're just left with this square root of 3. And same thing is true here. ln of e, that's our natural log of e, that's the same thing as log base e of e. ln is just a nice way of writing log base e of e. or sorry, log base e. So ln of e, that's going to cancel. Again, cancel isn't the right word exactly, but it's going to kind of go away, and you're just left with this exponent, which is 0.35t. And that's from the same property that was used in A. All right, we have some more properties here. You'll notice that these properties kind of mimic the exponential properties as well, which makes them a little easier to memorize, even though it's not super easy. But when you have two things that are multiplied, the log of a product is going to equal the sum of the logs. And this is actually very similar to exponents, right? If you have two things where you have the same base and the exponents are multiplied, you can turn that into addition. And then the same thing is true, quotient is going to be true for division. So you can basically break it up into two separate logs if you have something that's divided where they're subtracted from one another and you have a log attached to each. And then the log of a power equals the product of the power and the log. So if you have log base a of m to the r power, what you can essentially do is you can take this r, that's our exponent, and you can stick it out front, okay? So you can always think of, I always just kind of imagine it visually happening, this little exponent becomes a product. So what you do is you just take your r and you move it out front, and then you have an equivalent statement. Okay, so the first thing we're going to do with these is write a logarithmic expression as a sum or difference of logarithms. So essentially what we want to do is we want to go ahead and expand this. We're going to make it as large as we can. So let's say we have log base 2, and then we have x squared times the cube root of x minus 1. This is really nasty. But the first thing you want to do is you want to see that these two things, this x squared and this cube root of x minus 1, those two things are multiplied. Now, if you recall, multiplication can be turned into addition. So essentially what we do is we just keep this log base 2 attached to each thing. So we break it up so that we have log base 2 of x squared, that's our first part, plus log base 2 of cube root of x minus 1. Now, the next thing we want to do is rewrite any roots as powers, okay? So instead of having the cube root, we actually have the 1/3 power. And then you always want to write it so that you have your powers as factors. It'll say this, typically it'll say express all powers as factors. So what you do is you're going to take this power, which is 2, and you move it out front, so it becomes 2 log base 2 of x. And then you take this 1/3, which is your power, and you move it out front as well. So you have plus 1/3 log base 2 of x minus 1. And that's using this rule right here. Okay, let's try another one. Let's say we have log base 6 of x to the 4th over x squared plus 3 squared. Again, we want to express all powers as factors, and we want to express it as a difference of logarithms. So if you see, there's one sort of large division problem here. When you have division, you want to change it into subtraction. So what we do is we rewrite it as log base 6 of x to the 4th minus log base 6 of x squared plus 3 squared. And then we rewrite our powers as factors. So we take our 4, which was our power, and we move it out front, so it's now a factor. So we have 4 times log base 6 of x, and then we take our 2, which was a factor, and move it out front as well. So we have minus 2 times log base 6 of x squared plus 3. Okay, here's a particularly nasty looking one, except with natural log, which makes no difference in terms of how we solve it. So first thing we see is we see this big division problem. So anytime you see division, you want to go ahead and split that part up first. So what we have here is ln of x cubed times x minus 2, square root of that. So that was our numerator. And then we subtract whatever was in our denominator, again with this natural log or log, whatever it may be, attached. So we have minus ln of x plus 1 squared. And then if we look at this, we can also see that within this first part, this ln of x cubed times the square root of x minus 2, we have two things that are being multiplied. Now, if you recall, multiplication can be turned into addition. So really what we have here is ln of x cubed plus ln of the square root of x minus 2, which they've gone ahead and rewritten as x minus 2 to the 1/2 power. Please recall that anytime you have a root, you can rewrite that as 1 over whatever the root is. That would be your power. And then we have minus ln of x plus 1 squared. And so the last step would be to take all of our exponents and write them as factors. So we take our exponents and we basically just stick them out front. So we have ln of x cubed, so that becomes 3 ln of x. Then we had this part where we had the 1/2 as our power, so we stick our 1/2 out front. And this last part we had 2 as our power, so we stick that out front. So we're left with 3 ln of x plus 1/2 ln of x minus 2 ln of x plus 1. Okay, now here's another fun part, is basically they give it to you in reverse. So now they're going to give us something that's very long and nasty looking, and we have to write it as a single logarithm. So let's say we have something like this, 3 times ln of 2 plus ln of x squared. Now this is basically just the exact same problem that we did, but reversed. So the first thing we're going to do is take all of our factors, so all of the numbers that are in front, and rewrite them as powers instead of the other way around. So for this one, we have ln of 2 cubed, and then this stays the same, plus ln of x squared. Now if you recall, if two things are added and they have the same logarithm at the same base, then we can multiply them. So really what you have here is ln of 8x squared, since 2 cubed gives you 8. Now this one, again, we're going to rewrite our factors as exponents. So the first thing we're going to have is log base a of 4 to the 1/2 power minus log base a of 5 squared. And then if you recall, subtraction can be rewritten as division. And then if you have the 1/2 power, that's actually just square root. We know that square root of 4 is just 2. So really what we're left with is log base a of 2, which was our first part, divided by, since we have subtraction, and we know that 5 squared gives us 25. All right, for this last one, again, we're just going to start the same way. So we're going to rewrite all powers as exponents. So we should be left with log base a of 3 to the negative second power plus log base a of 2 cubed minus log base a of x squared plus 1. Not so bad so far. We're just taking the numbers that are out front and rewriting them as exponents. And then anywhere you see addition, you're going to want to write that as multiplication. So in our case, we have log base a of 3 to the negative 2 times 2 cubed, which we'll get to in a minute. And then we still have this minus log base a of x squared plus 1. Again, the subtraction you can write as division. So we change this so we have log base a, now 2 cubed times 3 to the negative second. We know that 2 cubed is going to be 8, so we're going to put that up here. We know that 3 to the negative second is 1/9, so instead of writing it as 8 times 1/9, which is not very nice, we can put our 1/9 in the denominator as long as we flip it over. So we really have 8 over 9, and then this minus that turned our part over here into division. So we are just left with x squared plus 1. So we've now written it as one nice logarithm. And again, the previous problems were just basically opposite. So they would give you something like this and have you work backwards until you get to this spot right here. Okay, a couple of other properties, and these might be a little more obvious, but basically if m is equal to n, then log base a of m is going to equal log base a of n, and that's also true the other way around. So if log base a of m equals log base a of n, then m equals n. So essentially, just like when we have the same bases for our exponents, if we have the same base for our logarithms, really what we can do is just ignore our logs because we know that the other numbers have to be the same. So let's learn how to evaluate some logarithms whose base is neither 10 nor e. So let's say we want to approximate log base 3 of 12, and we want to round our answer to 4 decimal places. We could change this so that we have y equals log base 3 of 12, and we could change this into exponential form so that we have 3 to the y equals 12. And then we could take natural log of both sides, so we'd have ln of 3 to the y equals ln of 12. Bring our exponents out front, so we have y equals ln of 3, and that's still equal, y times ln of 3 is equal to ln of 12, and then we divide both sides by ln 3, so our exact value would be y equals ln 12 over ln 3, and the approximate value would be 2.2619. Now, there is a much nicer way to do this, and that is the change of base formula. So essentially, if a is not 1, b is not 1, and m is a positive real number, then if we have log base a of m, What you can do is you can change it so that they have the same base, but essentially you've changed it into a division problem. So you have log base b, which is some base that you want of m, divided by log base b of a. Now this is the same thing that's down here, because if you recall, when we don't have a number written next to our log, like if we just have log of 5, it's implied that it's base 10, and that's what your calculator does. So what's shown down here is just a couple of the implied bases that, or typical bases that might be nice to use. So if b were 10, then you would really just have something like this. If b were e, you would have something like this, which is going to be natural log. So let's say we want to approximate log base 5 of 89. All we have to do is just take log of 89 and divide it by log of 5, or you can take ln of 89 and divide it by ln of 5. Now, you can't pick a log from one and a natural log from the other. You have to be consistent. So if you're going to use log of 89, you have to use log of 5. If you're going to use ln of 5, you have to use ln of 89. So you can't flip-flop them. But when you divide, either way, you should get about 2.7889. And this one over here, they try to confuse us a little bit by using some roots, but nothing's really any different. And again, they show it with a log or a natural log. And you get a value of somewhere around 2.322. So here is some nice, or a nice summary of the properties of logarithms. This can be found in your textbook as well. My suggestion would be to put any of these that you think you might have trouble with on a note card until you get used to them, or just keep writing them until you're comfortable with them. Really doing problems, though, is going to help you memorize these. It won't feel so much like memorization. Also, make sure to check and see what's provided to you on your final exam. That should be posted in that folder. Some of this might be. I don't recall off the top of my head. All right, last section is just using some of the things that we've already learned to actually solve some kind of complex equations. So these are some things to recall. We know all of this stuff since we just did it, so I'm not going to go over that again. So let's say we have log base 3 of 4 equals 2 times log base 3 of x. Now, when we have the opportunity to get possibly the same base, we want to go ahead and do that. So you'll notice these are both bases of 3, which is great. So what we want to do first is we want to take our 2, which is written as a product, and we want to change it into an exponent. So recall, anytime you have an exponent, you can bring it out front as a factor if you want. Anytime you have a factor out front, you're welcome to bring it up as an exponent. So what we have here is log base 3 of 4 equals log base 3 of x squared. And then if you remember, anytime you have the same bases, you can just drop the logs because we know that 4 has to equal x squared. And if we solve this, we get 2 or negative 2. Now, I cautioned you about ending up with more than one solution because of the fact that because the domain has to be positive numbers, we might have extraneous solutions, just like we did when we had roots. So if we try plugging negative 2 in, you'll notice is you have log base 3 of negative 2, which is no good. You can't do that in your calculator. It won't let you. There's a domain error. So negative 2 is extraneous, so your solution is just 2. All right, let's try another. Let's say we have log base 2 of x plus 2 plus log base 2 of x minus, 1 minus x, and that's equal to 1. Now, the problem with this one is that we have 2 different logs, so what we need to do is hopefully combine them in some intelligent way. Now, if you recall, if 2 things are added, we can change it into multiplication. So really, we just have log base 2 of x plus 2 times 1 minus x is equal to 1. We can go ahead and change this into exponential form, so we end up with 2 to the first power equals x plus 2 times 1 minus x. And if we FOIL this, we get 2 equals negative x squared minus x plus 2. Subtract 2 from both sides, so we get x squared plus x equals 0. And this can be factored into x times x plus 1. So we get 2 solutions of 0 and negative 1. Now, again, it's important to check. If we plug 0 in, we get 0 plus 2, that's 2, so that's fine. 1 minus 0 is 1, that's also fine. If we plug negative 1 in, we have negative 1 plus 2, that's a positive 1, which is fine. And 1 minus negative 1, which is 2, which is also fine. So both solutions are in the domain, so neither one of them are extraneous. We can also solve exponential equations. So this is another thing to recall. Remember, if you have the same bases, all you have to do is set the exponents equal to one another. So if you have 3 to the x equals 7, there's not really a way to get those bases to be the same. So we were doing some exponential equations in the beginning of the lecture where it was fairly easy, but this one there's no way to get 7 to have a base of 3. So what we need to do is we need to either take log or natural log of both sides. Just like you could square something or take square root, you can do the same thing with log or natural log. Now typically it's shown with natural log, but it doesn't matter at all what you do. You could use log base 10. So what we end up with is ln of 3 to the x equals ln of 7. And then we take our exponent, move it out front. So we get x times ln of 3 equals ln of 7. And then we're just solving for x, so we just divide by ln of 3. So our exact solution is going to be ln of 7 divided by ln of 3. And our approximate solution would be 1.771. Okay, now if we have something like this, 5 times 2 to the x equals 3, this looks really similar to the last one, except we have kind of an extra piece. So before we use what we know about logs and natural logs in order to get our exponent isolated, what we want to do is first get whatever is attached to this exponent by itself. So we want our 2 to the x to be by itself, so we divide both sides by 5. So we're left with 2 to the x equals 3/5. Now, when we're stuck with an exponent that is a variable, like in this case, we have our x as our exponent, in order to get rid of it, what we do is we take either log or natural log, just like we did in the last one, in order to get that exponent brought out front. So if we take natural log of both sides, we have ln of 2 to the x equals ln of 3/5. Go ahead and move that x out front, that's our exponent. So we have x times ln of 2 equals ln of 3/5. Divide both sides by ln of 2, which is not very nice looking, but that's okay. We get ln of 3/5 divided by ln of 2, and that's going to be approximately equal to negative 0.737. So this right here would be our exact answer, and then this would be our approximate. All right, this is about as bad as it gets, is something where we have x's in both exponents. So if we have 2 to the x minus 1 equals 5 to the 2x plus 3, in order to get rid of that, we're going to have to take log or natural log of both sides. So let's go ahead and take natural log. So we have ln of 2 to the x minus 1 equals ln of 5 to the 2x plus 3. Now if we recall, anytime you have an exponent, you're allowed to make it a factor. So we just bring our exponents out front. The thing you have to be super careful of, and we haven't seen any like this yet, but anytime you have more than one thing in your exponent, that's your entire exponent. So you need to make sure you put parentheses around it. So really we have x minus 1 in parentheses times ln of 2 equals 2x plus 3 in parentheses times ln of 5. And then we have to go about distributing. So we have x times ln 2 minus ln 2 equals 2x ln 5 plus 3 ln 5. So this really doesn't look nice at all yet. And then what you want to do, the nice thing about these is they always kind of work out the same way. So once you've distributed, you get everything with an x on one side and everything else on the other side. So we move our 2x ln 5 to the other side by subtracting it. We move our ln 2 to the other side by adding it. So we're left with x ln 2 minus 2x ln 5 equals 3 ln 5 plus ln 2. And then we factor out an x. So we're left with x times ln 2 minus 2 ln 5 equals 3 ln 5 plus ln 2. And then we can divide by this whole mess that we have attached to our x. So we're left with this really not very nice looking thing. 3 ln 5 plus ln 2, all divided by ln 2 minus 2 ln 5. So this would be your exact answer. And then this one right here is your approximate. I will kind of tell you guys, though, that that's about as bad as it gets. There aren't many equations that are much nastier than that one. There is this type as well, where we have something that looks like it might be in quadratic form. Okay, so this might not be automatically apparent, but hopefully you'll get used to seeing these. It's normally not the most typical type of question, but if we think about this, we know that 9 and 3 have kind of a special relationship because 3 squared is actually 9. So we could rewrite 9 to the x power as 3 to the x power squared. And because of this, our equation is actually just in quadratic form. So we know that u is going to be equal to this 3 to the x power. So we'd know that u squared is equal to 9 to the x power. So really what we're doing is we're just replacing all of our pieces. Instead of having x's, we're now going to have u's. So 9 to the x power, that's u squared. 3 to the x power is just u, and then we still have this minus 6. Now this is really easy to solve. U squared minus u minus 6, you can factor that. It's going to factor into u minus 3 times u plus 2. And if you solve it, you just get u equals positive 3 or u equals negative 2. But what we actually care about is what our x is, so we would need to substitute it back in. So we'd get 3 to the x equals 3, or 3 to the x equals negative 2. Now, if you think about this one over here, 3 to the x equals 3, that one's just going to be x equal to 1. This one is not going to work. 3 to the x equals negative 2. We know that 3 to the x has to be greater than 0 for all x because of what we know about domain and range. But for this one, we just get x equals 1, so that's going to be our solution. All right, that is it for this week. If you are interested in seeing this presentation later, feel free to send me an email. You should have my email from when you signed up from the webinar. You can email me, I can send you the link, but are there any other questions? I think there are a couple of people logged on. You can go ahead and type your question and then I'll see it pop up. So let me give you a minute in case anybody has any. It can either be over the material or how to access this. All right then, I don't think there are any questions for this week, so thank you for joining, and we'll be back next week to cover the rest of Chapter 6. I hope you guys have a good one.